Hello students, welcome to day 18 of PU2 Brahmastra series. So today is Thursday and it's time to study chemistry, right? So today we are going to discuss the most expected questions from the chapter D and F block elements. So if you watch this one video and do all the questions, remember all the answers, then this chapter is done for you. You do not have to go for any other source. Clear? So now coming to this, you can join our WhatsApp channel. Link is there in the description section. The PDF notes of this class will be updated there. Okay. So now let's get started. Today we are going to discuss first the mark distribution of D and F block. So this chapter is a high weightage topic because it has a total weightage of, you can see, 10 marks, right? So in that there are two 3-marker questions which accounts for 6 marks. There is one 2-marker question, so that is again like 8 marks, and there are 2 MCQs, so that is equal to 10 marks here. So now in this chapter you have to mainly do learning. Okay, there are few concepts also that you need to understand, okay, but basically this is like mostly like a theoretical. You have to learn the reasons, you have to learn some facts, okay. And one very important thing that you should remember before starting this chapter is you should have done the electronic configuration from scandium to zinc. This is mandatory. If you do not remember this one, then definitely you will not be able to solve even a single question from here. Okay, so now let us see the in this particular lecture what we are going to discuss. We are going to discuss among like 10 MCQs which are of HOTS type, that we will be discussing. 2-marker questions, 27 questions we are going to discuss. 3-marker questions around 23 we are going, so I can say we are total discussing 60 questions. So from this one chapter, if you practice the 60 questions, then definitely you will be getting total how many questions from this chapter? 1, 2, 3, 4, 5. So 5 questions you will be getting, and I am giving you 60 questions to practice, right? Then definitely you will be able to solve these all 5 questions. You can get 10 on 10 on this particular chapter, right? So yes, now let us go. Okay, one more very important information here, that you know we have launched the PU2 Success Blueprint test series. Okay, so this test series, the first test will be released on 15th of December 2024, and in this test series you are having 12 mock test papers, okay, and in that there are 4 part tests and 8 full length papers. You will be getting like all the subjects, that is PCMB is covered with computer science, and then you have this question paper is according to the recent blueprint that is released by the PU board, and it is according to the updated syllabus, and you will be getting video solutions and revision videos, and all your doubts in these mock test papers will be clarified, okay. And one more important thing, that remember the date, as I said you, the first test will be released on 15th of December 2024. So please mark this date. So you can join this test series by paying just rupees 599. It is after 50% off. So please students, do not delay. If you delay, and then the price may increase, so take the benefit of this discount. And if you want to join, the link is there in the description section. Go there, register and buy this as soon as possible. Okay, so fine. Now let us move towards the MCQ, that is 1-marker questions. Let us solve each of them. The magnetic moment of a transition metal is 15 Bohr magneton, okay. Therefore the number of unpaired electrons present in. So if you know, magnetic moment formula is root over of n into n plus 2, right, where n is your number of unpaired electrons, right. Now if I have here, this is 15, right, this n into n plus 2 is 15. So how can I arrange them? Just very simple. If I take n is equal to 3, then what will I get here? 3 into 3 plus 2, and that is 3 into 5, that is 15, right. So what is the n value? N value has to be 3. Very simple question. This formula what you need to remember. Question number 2. Potassium permanganate acts as an oxidant in an alkaline and acidic medium. The final products formed from the 2 conditions are respectively. So if you remember, manganese, okay, MnO4 permanganate, right, MnO4 minus, can is a very good oxidizing agent, so it will oxidize itself and will get reduced, right? It will oxidize others and itself it will get reduced. So in acidic medium it gets reduced to Mn2 plus, okay, and this is in acidic medium. And in your that is alkaline medium, it gets converted to MnO2. Okay, so first it is, so order you have to be very careful. First it is alkaline medium, that means MnO2, okay, and in acidic medium it is Mn2 plus, so option number D here. Clear? Next, question number 6. Number of electrons in 3D orbital Cr2 plus, Mn2 plus, Fe2 plus are 3, 4, 5 and okay, here it is not good, it is 4, okay, respectively. Which of the following ions will have the largest value of magnetic moment? So magnetic moment, just now we discussed, will depend on the number of unpaired electrons. So if you see Mn2 plus has 5 unpaired electrons, maximum number of unpaired electrons is there, so that is why it will have highest magnetic moment, right? So that is why correct answer is option number C here. Next is question number 4. The correct order of E0 values with negative sign for the 4 successive elements Cr, Mn, Fe and Cn. Okay, see, this question is very, very important. You are asking the correct order of M2 plus to N, that is the reduction potential with negative sign. Means what? See, generally if a metal is ready to get reduced, okay, from M2 plus to M, okay, if it can undergo reduction easily, then the E0 value will be positive, right? But if it is asking negative sign, that means this value is negative, that means the metal does not want to get reduced, does not want to get reduced. In that case the value will be negative. Now if you see these elements, manganese Mn2 plus configuration is 3d5, right, which is a half filled and a stable configuration, right, which is a half filled and stable configuration. So that is why what happens, this Mn2 plus to M, like it will, this value to M will be negative, okay, because it doesn't want to get into this transition, okay. So that is why Mn will have highest value, only one option is correct, so A is the correct answer. Once again I want to repeat here, the correct order of the values of negative sign for the 4 successive, okay, negative sign means you have to think which element will not undergo this transition from Mn2 plus to Mn, which one will not undergo, will have the highest negative value, okay. So that is why the highest negative value will be for manganese, because it is very stable in Mn plus 2 state, it doesn't want to go to Mn state, okay, M2 plus to M state, okay. So option number A. Okay, next, the correct order of ionic radii. Okay, so it is a increasing order, right? So you know these all are belonging to one period, right? In one period. So size decreases along the period, right? So and you just, if you do not know anything also, you should know that lanthanum is the starting element, right? And lutetium is the ending element, right? So definitely the size of lanthanum will be highest, right? There is only one option with this, so correct answer will be option number D here, okay. Next, question number 6. Na2CrO4 with in presence of A will give you Na2SO4 and B, that is an orange compound, then with KCl you get C plus NaCl. So if you can see, this reaction is from the, this equation is from the preparation of K2Cr2O7. Very, very important question. So here what happened, first of all Na2CrO4 is converted to Na2SO4, that happens in presence of H2SO4, okay. We can eliminate these two options. Then here you get another, that orange compound that you form is your potassium sodium chromate, right, sodium dichromate. This is sodium chromate, it gets converted to sodium dichromate, this option is wrong. Then sodium dichromate is converted to potassium dichromate. So option number D is the correct answer here. Next question number 7 is from the reactions of lanthanoids. So lanthanoids with water, okay. So what will happen? It will form OH. From water it gives OH and lanthanum oxidation state is +3. If you do crisscross, I will get LnOH3, right. So X is LnOH3. We have option number B and D, right. It can be either option number B or it can be option number D. Sorry. Yeah, only option number B, I think. Yeah, here also it is LnOHO3, so we can eliminate this one. Next, if you see with oxygen, so again if you see Ln is +3, oxygen is -2, so what will happen? We will get Ln2O3, right. So that is there, Ln2O3. And then reaction with acids, so metals with acids will give you what? Hydrogen gas. So H2 gas, option number B is the correct answer here. With only first one you can find out or guess the answer. Question number 8. We have V2O5 reacts with acids as well as alkalis to give dash and dash, okay, respectively. So when it reacts with acids you get VO4 plus and with alkalis you get VO4 3 minus, okay. Option number A is correct. So remember V2O5, okay, with acid and with alkali, right. With acid it gives you VO4 plus and here it gives you VO4 3 minus, okay. Now if you check the oxidation state here, this is vanadium is +5 and here vanadium is in okay, VO4 plus and okay. So here we get +5 oxidation state and from here it gets converted to VO4 plus and here it gets converted to VO4 3 minus. There is nothing related to oxidation state, so we do not have to worry that. Just you have to remember in acidic state it is VO4 plus, in alkaline medium VO4 3 minus, okay. Option number A. Question number 9. The electronic configuration of yttrium is 4F14 5s2 and that of lutetium is 4F14 5d1 and 6s2 can be explained on the basis of extra stability of half filled. No, there is no extra stability of half filled here. Extra stability of fully filled orbitals. Now see, in case of this one, okay, so there is no adjustment done. This configuration comes if you follow the natural rules of filling the atomic orbitals. So that is why even this is not the correct answer. The correct answer is the usual rules of arrangement of electrons in their orbitals. Option number C, okay. Next, last question of MCQ. Which of the following graph shows correct trend in the size of +3 ions of lanthanides? So if you see it along the period, okay, along the period what happens? Along the period size decreases and due to of lanthanide contraction, right. So you can see from here lanthanum to lutetium size is increasing, this is not correct. Here lanthanum to lutetium there is a linear increase, this is also not correct. Here there is decrease and increase, this is also not correct. This one is correct, there is exponential decrease. So option number B is the correct answer, okay. So these questions were really of HOTS type, so make sure that you read every line of this book properly, of this chapter correctly, okay. If you're doing the next, I am saying all 50 questions I have discussed, all those questions if you would able to do, then definitely you can solve these 10 MCQs also. Fine, let us start with the first question. On what ground can you say that scandium is a transition element but zinc is not? Okay. So first of all, let us do a little revision. What is the meaning of a transition element? Transition elements are those elements which have partially filled d orbitals in either in their ground state or in the common oxidation state, okay. So they should have what? Partially filled d orbitals. When? In two cases, either in the ground state or in the common oxidation state. If they do not have partially filled d orbitals either in the ground state or in the common oxidation state, then they will not be called as a transition element. They are definitely d block elements, but they are not transition elements, okay. So with this definition we can definitely answer this question. Can you say that scandium is a transition element? So scandium electronic configuration, I told you electronic configuration is very important for this particular chapter. Scandium electronic configuration, if you see, that is that is scandium is 3d1 and 4s2, right? Now if you see in the ground state only it has one unpaired electron, so definitely it is a transition element. But if you see zinc configuration, it is what, 3d10 and 4s2, right? That it has 10 electrons, so that is there is no unpaired electron in the ground state. Now let us see in the common oxidation state, that is Zn plus 2 state. 2 electrons will go from here, still it has 3d10, right? So zinc does not have partially filled d orbital either in the ground state or in the common oxidation state. So that is why zinc is not a transition element. Okay, so you can see the answer here, scandium contains partially filled d orbitals, so it is considered as a transition element. Zinc contains completely filled d orbitals in its ground state and in its oxidation state, hence it is not a transition element. Clear? Very simple question. Next, silver atom has completely filled d orbital 4d10 in its ground state. How can you say that it is a transition element? Again the same thing, we know it should have partially filled d orbital either in the ground state or in the common oxidation state. Now silver has fully filled d configuration in the ground state, but in its common oxidation state, that is in Ag plus 2 state, it has partially filled d orbital. Okay, we'll see here. Silver can exhibit plus 2 oxidation state wherein it will have incompletely filled d orbitals 4d, and hence it is a transition element. Clear? Because it is having unpaired electron in the common oxidation state of plus 2, so that is why it is a transition element. The same question can be asked for copper. So if you see, copper electronic configuration is 3d10 4s1 in the ground state. Copper can also have plus 2 oxidation state, and in that case it will get 3d9. So in the common oxidation state it has partially filled d orbital, so that is why copper can also be called as a transition element. Okay, fine. Now let us move towards the second question here. Explain the variation of atomic and ionic sizes of the transition metals. Okay, so here you have to tell about the size of the atomic elements. So this is very important question. So first of all, what happens, see the answer carefully. The atomic and ionic radiuses decreases with the increase in atomic number, but there are variations. Okay, generally it should decrease with the increase in atomic number. Even in normal periodic table we know that along a period size decreases, right? But here certain variations are there. What is that? See, in the 3D series the atomic radius decreases from scandium to chromium. Okay, up to chromium the size decreases due to the increase in effective nuclear charge, right? There is a nuclear charge is increasing, size will decrease, that is common thing which happens generally in every period. But after chromium what happens? From chromium to copper the atomic radius remains almost same. This is because the increase in effective nuclear charge is compensated by the shielding effect or the screening effect. Now see, when you are moving from chromium to copper, the d electrons are filled, right? These d electrons do inter-electronic repulsion, okay, and they try to increase the size of the atom. The effective nuclear charge tries to reduce the size, d electrons are there, they try to increase the size. So as a result of this there is a balance between both of them and the size remains constant up to copper. Now after copper what happens? Zn has larger atomic radius than copper due to the completely filled d orbitals. Now in the copper, in the d orbital there is all 10 electrons are present. Now what will happen? The inter-electronic repulsion factor predominates over the effective nuclear charge, right? So that is why the size will increase. Okay, so that is this question. Next, along the, so if you have understood this one, that, so listen, for size we have two factors. Okay, one is your effective nuclear charge and is inter-electron repulsion. Now as we move in the beginning, this is, so this will try to decrease the size and this will try to increase the size. So in the beginning this is very dominant, the size was decreasing. From chromium to copper these both are equal, so size remains constant. One tries to decrease, another tries to increase. So in that case what happens? The size remains constant. Then after this one, this factor is dominant, so from copper to zinc size is increasing. Okay, Next, along the period the density increases gives the reason. So along the period the density is increasing, that is because mass is increasing, size is decreasing, right? This is due because the decrease in metallic radius due to the increase in effective nuclear charge. So size is decreasing, right? Density is equal to what? Mass by volume. So if the size will decrease, volume will decrease, density will increase. Clear? Okay. Now let us go to the next question. Explain the variations of ionization enthalpy in the D block elements. Okay. So ionization enthalpy, generally what happens along the period, it increases due to the increase due to the increase in the effective nuclear charge, or you can say decrease in the radius. So the same thing happens here. It increases along the period due to the increase in effective nuclear charge. Okay. Next, what is the reason for irregular variation of ionization enthalpies in the first series of the transition elements? So why? But we will see certain ionization enthalpies is not constant. It is not decreasing. Sorry, it is not increasing constantly along the period. That is because of some stable configuration that comes in between the series. Okay. So why the ionization enthalpies is irregular, that is due to the stability of different configurations. Okay, about this we will do in the next question, very in detail we will be solving. Question number 4, very important. This is the most important question in this whole video, I can say. Second ionization enthalpy of chromium and copper are sufficiently higher than their neighbors. Okay, so I told you for every question of ionization enthalpy you should be knowing the electronic configuration. Chromium electronic configuration is what? 3d5 and 4s1. Copper electronic configuration is 3d10 and 4s1. The second ionization enthalpy. Now see, second ionization enthalpy means already one electron is removed. So if I remove one electron from here, I'll get Cr plus, right? And the configuration will be 3d5. And from here, if I remove one electron, configuration is Cu plus and the configuration is 3d10. Now you see, can you see something special about these configurations? These are exactly half filled and fully filled configuration, which are very stable. So to remove electron from these configurations, you will require more energy. That is why the second ionization enthalpy is very high. Clear? Now next one, the first ionization of enthalpy of chromium is lower. Yes, now if you see the first ionization enthalpy of chromium, 3d5 and 4s1. So it is the question is asking this if you want to remove one electron from here, you can do it very easily when the ionization enthalpy is lower. Okay, one key point here, if ionization enthalpy is lower, that means electrons can be removed easily. Okay, now so if I want, I'll get 3d5. So the question is asked why this ionization energy that you are putting here to remove this one electron is very less. That is because once this electron is removed, chromium will get a stable half-filled configuration, right? It wants to get rid of this one electron so that it can gain this half-filled configuration. So that is why this value is very low. Okay, this is done. Next question. The second ionization enthalpy of zinc is less than the second ionization enthalpy of copper. Okay, let us again see second ionization enthalpy of zinc. So zinc configuration is 3d10 4s2 and copper is 3d10 4s1. The question is telling that the second ionization enthalpy of zinc is less than the second ionization enthalpy of copper. Again the same thing, if you remove one electron from here, you will get Cu plus, whose configuration is 3d10, right, which is a very stable configuration. Now if you want to remove another electron from here, that is 3d9, you are disturbing this stable state, right? So that is why here you will have to require much more energy, right? But if you see in Zn, first one electron is removed, you get 3d10 4s1. Another configuration, if you remove, still the configuration is 3d10, there is no change in that, right? But if you copper, if you remove one more electron, this stability will be lost, right? So that is why the second ionization enthalpy of copper is very high. Okay, next question, it is continuing. Okay, some more reasoning question here. Second ionization enthalpy of manganese is less than that of the iron. Okay, so now if you see, manganese configuration is 3d5 4s2, okay, and iron configuration is 3d6 4s2. You removed one electron from here, we get 3d5 4s1. You remove another electron from here, you get 3d5. Okay, and if you talk about one electron you remove from here, okay, you will get 3d6 and 4s1, and if you remove one more electron you get 3d6, right? So now you see the second ionization enthalpy, right, here of manganese is less than the second ionization enthalpy of iron. Now see here what happens. Again the same thing, manganese wants to get rid of this one electron, right? If it is getting rid of this one electron, it is gaining a stable half-filled configuration. So I told you, if so, that is why what I can say, the removal of this one electron will be very easy. Why? Because it is gaining a stable configuration, right? So this change will be very easy. So if the change is very easy, if the electrons can be removed easily, then ionization energy will be low, right? Next, if you see question number E here, the third ionization enthalpy of manganese is more than that of Fe. Now we'll go for third ionization enthalpy. So if you see from here, if I continue, this is 3d5 for manganese after Mn plus 2, right, and Fe plus 2 is 3d6. Now if I want to remove one more electron, I'll get 3d4. Here if I want to remove one more electron, I'll get 3d5. So this is your Mn plus 3 and this is your Fe plus 3. Now again you see here, if you remove one electron from here, you are getting a stable half-filled configuration, right? So you want to get rid of that one electron so that you can get a half-filled configuration. So this metal will easily try to give out that one electron. So if the electrons can be removed easily, then definitely ionization energy will be lower here. So that is why the third ionization enthalpy of manganese will be more here. Now why manganese will be more? See, if you remove one more electron, this configuration was stable, right, and this configuration is unstable, right? But so that is why when you want to remove, the metal doesn't want to get rid of this one electron, because if you remove that one electron, it will become unstable, right? So metal wants to hold that electron very, very tightly, but you want to remove it, then you have to give more energy here, right? But here the metal wants, okay, if you want to come, take this electron and go, so that I will be stable, right? That is what iron will be thinking. Manganese, how it will be thinking, please do not come, don't take this electron, I will become unstable here, right? So here what will happen, like ionization enthalpy will be very high, here the ionization enthalpy will be very less. I hope you are getting this. Next, third ionization energies of copper, nickel and zinc is very high. So that is very simple, because these elements are found in +2 state, or are stable in +2 state. Their +3 state is very, very rare, or it is very difficult to find them in +3 state. So that is why you cannot remove one electron. If you want to remove, you have to provide very high energy. So now students, in these type of questions, you do not have to remember these answers at all. The only thing that you need to use is your logic. If anything is coming from unstable to stable, right, I'm talking about ionization enthalpy. Stable to like it is unstable and it is gaining stability by removing one electron, like for example +3 to Fe, +2 to +3. If you remove one electron, it is gaining stability. In that case, metal will be very happy to give you that electron, and ionization enthalpy will be low. Now if by removal of electrons the metal is becoming unstable, then it will not be ready to remove that electron, and you have to put more energy there, ionization enthalpy will go high. I hope this concept is very clear. Okay, now let us move towards the next question. Explain the variable oxidation state of transition metals. The question previous was, you need to explain the variable ionization enthalpy. And here the question is about oxidation state. So transition metals have a variety of oxidation states. That is due to the participation of both N-1d and Ns electrons in the bond formation. Okay, so due to the loss, okay, once again, due to the loss of electrons from both N-1d and Ns electrons, as they have similar energy. Okay, next, name the element of the 3D series which shows the maximum or highest oxidation state. So manganese shows the maximum number of oxidation states from +2, +3, +4, +5, +7, and it also shows the highest oxidation state. Okay, so no other elements of 3D series has oxidation state more than 7. Okay, next question, name a transition element which does not exhibit variable oxidation state. So here there can be one answer is zinc, another answer can also be scandium. Okay, scandium also shows only one oxidation state, that is +3. Zinc only shows one oxidation state, that is +2. Okay, clear? So here you should remember two questions are there. If it is asked which has the highest oxidation state, then also manganese. Which has the maximum number of oxidation state, then also it is manganese. Okay, these questions can be asked very easily in MCQs. Okay, this is also very important. Next, question number 6. Why Cr2 plus is reducing and Mn plus 3 is oxidizing when both have D4 configuration? Okay, now see, Cr2 plus, okay, Cr electronic configuration is 3d5 and 4s2, sorry, 4s1, 3d5 and 4s1, and Cr plus 2 is 3d4. Okay, and here for manganese, manganese is 3d5 4s2 and manganese plus 3 is 3d4. Okay, both are having 3d4 configuration. Now they are saying that Cr2 plus is reducing, means it will reduce others, itself it will undergo what? Oxidation. And oxidation means what? Loss of electron, right? So if it loses one electron, it will become Cr plus 3, which is D3 configuration. Okay, and they are saying that Mn3 plus is oxidizing, it will oxidize others, itself it will undergo what? Reduction. If it is undergoing reduction, what will happen? It will gain electron. If it gain electron, what will become? Mn2 plus, configuration will be 3d5. I hope now you can answer this question very easily. So here you see, when Cr2 plus gets converted to Cr3 plus, it gives 3d3 configuration, which is a stable configuration of T2G. Now this, what is T2G, you will understand in the coordination chapter. It will get a configuration of T2G, which is half-filled configuration. Similarly, if manganese is oxidizing others and itself it is getting reduced, it will get half-filled configuration, right? So that is why Cr2 plus is oxidizing, whereas manganese 2 plus, sorry, Cr2 plus is a reducing agent, itself it wants to get oxidized. Mn2 plus itself it is going reduction, it will behave as an, sorry, itself it is going reduction, it will behave as an oxidizing agent. Okay, so you can see here Cr2 plus is reducing because its configuration changes from D4 to D3. Okay, so if it is reducing, it will reduce others, itself it will get oxidized. Oxidized means loss of electrons, right? So the configuration, loss of electrons means +2 to +3. Configuration changes from D4 to D3, right? The latter has an half-filled T2G level. Now similarly, Mn3 plus is oxidizing because the configuration changes from Mn plus 3 to +2. If it is oxidizing, itself it will undergo reduction. Reduction means gain of electrons. Mn plus 3 plus 1 electron, Mn2 plus, configuration changes from D4 to D5, which is a half-filled configuration with extra stability. Okay. Next, why is the highest oxidation state of a metal exhibited in its oxides or fluorides only? So this is also very important question. Generally, the transition elements have their highest oxidation states with fluorides or oxides. Now the reason for this one is both oxygen and fluorine are highly electronegative and have very small size. Okay, so highly electronegative and very small size. That are the two reasons. Due to these properties, they are able to oxidize the metals in their higher oxidation state. Okay. Next, question number 7. Which is a stronger reducing agent between Cr2 plus or Fe2 plus, and why? Okay, stronger, so you have Cr2 plus and we have Fe2 plus, right? So let me, one second, okay, let me write down here so that I won't overlap. Cr2 plus and Fe2 plus. Cr2 plus, what is the oxidation number, or you can say what is the electronic configuration? 3d4, right? If it is a reducing agent, it will reduce others, itself it will get oxidized. Oxidized means there will be loss of electrons and it will become Cr3 plus, right? Configuration is 3d3, and if you remember, this is P2G half filled configuration. Okay, now if you see the next one, that is Fe2 plus, Fe2 plus has a configuration of 3d6. Now if it is undergoing reduction, a reducing agent, itself it will undergo oxidation, it will lose one electron. Fe3 plus is 3d5, which is also stable, half filled, right? But out of these two, this is more stable. Okay, the reason, again, if you have learned coordination chemistry, you know d orbital, then T2G orbital level, energy level is less than the d orbitals, right? So that is why they are more stable. So that is why this one will be a stronger reducing agent. Okay, so Cr2 plus is a stronger reducing agent than Fe2 plus. This is because the configuration of Cr2 plus changes from D4 to D3, and D3 is a stable due to the half filled T2G level. Clear? Okay, next is question number 8 here. Between MnO and Mn2O7, which one of these has more covalent character? Very simple. If more oxidation state, then more covalent character. Okay, so here if you see oxidation state is +2, here it is +7, more oxidation state, more is the covalent character. Okay, so Mn2 plus higher oxidation state will show higher covalent character. Next, arrange this following in the increasing order of their acidic character. So here also you should remember higher oxidation state, okay, that will imply high acidity. Higher oxidation state, high acidity. So here if I see what is the oxidation state here, that is +3, here it is +6, and here it is +2, right? Higher oxidation state, higher acidity, so CrO3 will be maximum, then you have Cr2O3, and then you have CrO. Okay. Next, question number 9. How would you account for the increasing oxidizing power in the series? Okay, oxidizing power. Now I will just tell you the story behind this. Oxidizing power means what? It will oxidize others. Itself it will undergo reduction. Reduction means it should gain electrons, right? So if I do not have any electrons, okay, if I am in the high, like when you have lost so many electrons, your oxidation state will be high. If you lose one electron, +1, 2 electrons, +2, 3 electrons, +3. So when you have lost so many electrons, you can also gain so many electrons. But if you have lost only one electron, will you be able to, or will you be attracted to gain electrons? No, right? So the same thing happens. If you see here, the oxidation state is VO2 plus, right? So the oxidation state here is plus, I can write X minus 2 is equal to, vanadium is +4, and here if you see that is +6, and here it is MnO4, this is 2 minus, so this one, no, MnO4 minus, so this is +7, right? So higher is the oxidation state, means it has lost many electrons, that means it can gain many electrons. If it gains many electron, it is undergoing reduction. If it is undergoing reduction, it will behave as an oxidizing agent. Okay, so that you can explain. This is due to the increasing stability of the lower species to which they are reduced. Okay, the stability after gaining electrons, they will gain more stable configuration. Here many copper compounds are unstable in the aqueous solution and undergo disproportionation reaction. So copper plus, if you see, they undergo disproportionation reactions to give you copper plus Cu2 plus. Okay, here to here is what? Reduction, and here to here is oxidation. Now so the question is, why this copper plus is unstable in the aqueous solution even though they have D10 configuration? Why does it go to Cu2 plus? So that is because Cu2 plus in aqueous solution is more stable due to high hydration enthalpy. Okay, so you can see the stability of Cu2 plus ion is more than Cu plus ion in aqueous medium. This is due to the formation or due to more negative enthalpy of hydrogen of Cu2 plus than Cu plus, which is more than the second ionization enthalpy of copper. So when they go into the aquatic medium, okay, so copper 2 plus loses more energy, and if it loses more energy it becomes more stable, right? So the hydration enthalpy of copper 2 plus is more, that is why that is more stable, and that is why copper plus converts to copper 2 plus. Okay, fine. Next, question number 10, calculate the magnetic moment of scandium 3 plus. So this is very simple question. If you remember, magnetic moment formula is root over of n into n plus 2. Scandium 3 plus has no unpaired electron. No unpaired electrons means n is equal to 0, so magnetic moment will be 0. Next, calculate the magnetic moment of Ti 3 plus. So if you see, this is suppose B, okay. So scandium titanium, right? Titanium is 3d2 4s2. Titanium 3 plus means 3 electrons are loses, so first 2 electrons will lose from here, then 1 electron will lose from here, so I'll get 3d1, right? Ti 3 plus has 3d1, so 1 unpaired electron, so if I put like this 1 into 1 plus 2, so that is root over of 3, that is 1.7. Okay. Next, calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. Calculate the magnetic moment of a atomic number is 25 means it is manganese, right? Mn2 plus divalent ion. Mn2 plus configuration is d5, unpaired electrons is 5, so root over of 5 into 5 plus 2, that is root over of 35. You can calculate this one or you can just write like this. Next, calculate the spin only magnetic moment of M2 plus Z equal to 27. So 27 is your cobalt, right? So cobalt, if you see, it is 3d7 4s2. Now cobalt 2 plus is 3d7. So if I write 3d7 configuration, right? So 1, 2, 3, 4, 5, 6 and 7, number of unpaired electrons is 3. So magnetic moment will be 3 into 3 plus 2, that is root over of 15. Okay. So like this, many questions can come, any atom can come. The only thing you need to know is you need to remember the electronic configurations. Okay. Fine. Next, question number 11, which of the following is colored compound? So for colored also you should remember that it should have unpaired electron. If no unpaired electron, then it will be colorless. So you know, just now we discussed scandium 3 plus has no unpaired electron, so that is a colorless compound. Similarly, Zn2 plus has D10 configuration, no unpaired electron, that is also colorless. Chromium 3 plus has unpaired electron, right? Chromium electronic configuration, if you see, that is 3d5 4s1. Then chromium plus 3 means you 1 electron from here, 2 electrons from here, so I'll get 3d3, which is having 3 unpaired electrons, so that is why this compound will be colored. Next, name a transition element in 3D series which is colorless in both atomic state and in the oxidation state. So definitely that has to be zinc. So we already discussed zinc has no unpaired electron in the common state or in the common oxidation state or in the ground state. Okay. So that is the answer here. Next, transition metals forms a large number of complex compounds, give reason. So transition elements form a large number of complex compounds. This question is also very important. So you need to remember 3 reasons. It can be asked in a 3-marker question or can be asked in a 2-marker question. That is due to the smaller size. Okay. Then you have availability of vacant d orbitals, larger ionic charge. Any 2 points you can remember. Okay. Small size, vacant d orbitals, larger ionic charge. Next, catalytic activity of transition elements. You can see how often this question is asked. So here also you should remember 2 to 3 points. First one is your variable oxidation state. You can remember the common points in both. So here what was the point? Smaller size and availability of vacant d orbitals. So here first of all you can also search that one, presence of incompletely filled d orbitals, then variable oxidation states, then you can write formation of intermediate compounds. Okay, any 3 points you can learn from here. Example, if you have is asked, you can remember vanadium pentoxide is used in contact process. The contact process is the manufacture of H2SO4. Okay, next is formation of interstitial compounds. So first we discussed about the catalytic property. The previous to that was regarding the, what was that question? One second. Yeah, they form large number of complex compounds. Then is your catalytic property, and the next one is your interstitial compounds. So why they form interstitial compounds? So first of all, question, I have mixed all the answers here. Question can be like what are interstitial compounds? Explain the properties of interstitial compounds. So anything is asked, you need to answer this. Okay, if a question is asked what are interstitial compounds, the compounds in which the small atoms like hydrogen, carbon or nitrogen are trapped into the cavities of the crystal lattices of metals. Such compounds are called as interstitial compounds. Okay, so there are big lattices, in some small spaces, in some small gaps, small atoms go and occupy those places. That is called as interstitial compounds. Example can be asked, this only this much can be asked as a 2-marker question. TIC MnO4C. Remember easy examples, you do not have to remember these complex examples. TIC MnO4C. Next is their properties. So what changes happen if they form interstitial compounds? The first thing is okay, what are their physical chemical properties? They have high melting point now. Okay, if the interstitial compounds are formed, they form high melting point. Then they are chemically inert, they retain the metallic conductivity. Okay. Next, explain the formation of alloys of transition metal. So they are able to form alloys because of similar size. That's all the reason, right? So the transition elements have strong tendency to form alloys because their atomic sizes are very similar, and in the crystal lattice one metal can be readily replaced by another. Now alloys have high melting and boiling point. This is also not required point. Here some examples are there that you should remember. For stainless steel it is iron, carbon, chromium and nickel. For amalgam it is mercury with any other metal, brass is copper plus zinc, and bronze is copper plus tin. Okay. So next we'll go to some important compounds. Here you have 2 important compounds, that is KMnO4 and K2Cr2O7, right? So their formations you should remember definitely. So let us see the first question. When okay, here vanadium pentoxide is amphoteric oxide. Explain. Give an example for amphoteric oxide. So amphoteric oxide means they will undergo both oxidation, they can react with both acids and bases, right? So if you remember, we have discussed this question in the MCQ also, right? V2O5 reacts with both alkalis as well as acids to give you VO4 3- and VO4 plus respectively. Hence vanadium is an amphoteric. Any other example of amphoteric? Cr2O3. Okay. Next, coming to the most important, that is important compounds KMnO4 and K2Cr2O7. Give 2 uses of potassium dichromate. This time uses based questions are also asked in the midterm paper, so you should know some uses. So K2Cr2O7 used in leather industries and used as an oxidizing agent, used as a solvent, you can write down. Next, write the structure of chromate ion and dichromate ion. So chromate ion is CrO4 2-, right? So we have Cr, then this is a tetrahedral structures, okay, that is CrO4 2-. Next you have Cr2O7 2-, okay, dichromate. So here the structure is like this. We have chromium, you have oxygen, okay, and you have connected to another oxygen, and then you have oxygen. Okay, so both are what? Tetrahedral geometry. Okay. Next, okay, one more thing. Yeah, I have forgotten to put double bond. This is like this. Yeah. Okay. Next question number, explain the interconversion of chromates and dichromates ions depending on pH. Okay, so I'll be showing the answer, but I can tell you CrO4 2- and Cr2O7 2-, right? I think yeah. So here to here Okay, so if you give chromate and if you put acid on that, you get dichromate, and from here to here, if you get basic, you will get chromate, and chromate is yellow in color, okay, and dichromate is orange in color, right? So that is what in acidic medium, okay, in acidic medium, chromate is converted into dichromate. If you give acidic medium, chromate will be converted to dichromate, and in basic medium, dichromate is converted to chromate, okay, hence dichromate and chromate are interconvertible. Next, give laboratory preparation of KMnO4, okay, laboratory preparation of KMnO4. So in laboratory, the potassium permanganate is obtained by the oxidation of manganese iron salt, that is peroxodisulfate, okay. So here is the reaction, Mn2 plus S2O8 minus H2O give MnO4 minus SO42 minus 16H plus. You need to remember this reactions, very important, okay. Next, what is the structure of MnO4 2 minus and MnO4 ions? What is the action of heat on KMnO4, okay. So first, if you see the structure, I'll be telling you this one first. Let us draw the structure. MnO4 2 minus, okay. So the structure is like this. This is MnO4 2 minus, and MnO4 minus structure is like this. You have, okay, this is MnO4 2 minus, you can see 2 negative charges, and this is MnO4 minus 1 negative charge. Action of heat on KMnO4. So KMnO4, if you heat it, you get K2MnO4, MnO2 and O2. So remember this reaction also, K2MnO4 is your, see, this is KMnO4, this is K2MnO4, MnO2 and O2. Here the oxidation state is +7, okay, MnO4 minus, this is permanganate and this is manganate, okay, and here the oxidation state is +6, okay, MnO2 and O2, okay. Next question, yeah, permanganate titrations in presence of HCl are unsatisfactory. Why? So we already know that permanganate ions are very good, very strong oxidizing agents. So when you have chlorine, HCl, it converts Cl minus to Cl2, or it oxidizes Cl minus to Cl2, okay. And next we have that between KMnO4 and K2Cr2O7, which one of these is used as a primary standard in volumetric analysis? So that is your K2Cr2O7, okay. So here, because HCl is oxidized to chlorine, okay. Next is question number 23. What are lanthanoids? And write the general electronic configuration. So you know what is lanthanoids? The elements from Z is equal to 58 to lutetium. So this is your lanthanum, sorry, cerium, right? So elements from cerium to lutetium are called as lanthanoids. In these elements, the electrons are added in the 4f shell or 4f orbitals. Next, write the general electronic configuration. So Xe 4f1 to 14, 5d 0 to 1, 6s2. So you should remember the general electronic configuration. Next is, what is the common oxidation of lanthanoids? Why EU and YB shows +2 oxidation state. So common oxidation state is +3, but these two elements, okay, EU and YB 2+ and YB shows +2 oxidation state because they get a stable configuration. You can see here EU shows +2 oxidation state to attain the half filled 4f7 configuration, and YB to get fully filled, that is 4f14 configuration, okay. Next, what is the composition of mic metal? Give its use. So mic metal is a like alloy. So lanthanide 95%, iron 5%, okay, and traces of sulfur, carbon, calcium and aluminium are called as mic metal. Now what is its use? It is used in Mg based alloys to produce bullets, shell and lighter flint, okay. Uses, please remember, this time questions are asked repeatedly, so make sure that you learn these answers properly, okay. Next, question number 26 is about actinoids. What are actinoids? So the elements from thorium, that is 90, to lawrencium 103 are called as actinoids, and in these elements the electrons enter to the 5f orbitals, right. Next, general electronic configuration, Rn 5f1 to 14, 6d 0 to 1 and 7s2, okay. Next question number 27, 5f electrons will be more effectively shielded from the nuclear charge than the 4f electrons of the corresponding lanthanides. Give reason. Okay, the question is asked here that in the same lanthanoid, suppose we have electrons in the 4f orbital also and electrons in the 5f orbital also. So the 5f electrons will be more shielded, right, because they are outer, they are far away from the nucleus. Shielded means what? Anything which does not get the nuclear charge or which do not experience the nuclear charge. So because the 5f orbitals are present farther away, they do not, the 5f electrons do not experience the nuclear charge, right. So that is why they are more shielded. So because in actinoids the outer electrons are less firmly held and are available for bonding. Next, actinoid contraction is greater, that is because the 5f shielding or the 5f orbitals have poor shielding effect than 4f orbitals. Okay, so actinoid contraction is greater than lanthanide contraction because the 5f orbitals in actinoids have poor shielding effect than 4f electrons. So in both 4f and 5f have poor shielding effect, right. So that means, see, suppose here you have lanthanide, here you have 4f orbital and here you have valence electron. Okay, now this one is having, sorry, okay, one second, so I'll draw like this. Okay, so because these these electrons are like I can say are poor shielding effect, they do not shield properly. Okay, they are not like shielding properly the nuclear charge, they are poor shielding effect. So what I'll draw like this. So this nuclear charge, sorry, one second, yeah, so what happens, this nuclear charge reaches to this last electron but very less nuclear force is experienced by this electron. Why? Because the shielding effect is poor. But now if you consider actinoids, okay, so actinoids are there, then you have this one 5f orbitals. Okay, their shielding effect is worse than this one, right. This last electron is present here. So in that case what will happen, these electrons, this nuclear force can easily reach the last shell, right, they can pull the electrons better. So that is why actinide contraction is stronger than lanthanide contraction. Why? Because 5f have poor shielding effect than 4f. Clear? Okay, now we'll move towards the 3 marker questions. Some basic questions we'll be doing here. What are transition metals? Give reason that D block elements are called as transition elements. Why zinc, cadmium and mercury are not regarded as transition elements. So I hope all of you would have answered the last question by now. So transition elements are those elements which possess partially filled D subshell either in their atomic state or in the common oxidation state, right. Next, D block elements are called as transition elements because they lie between S and P block. The properties of the transition elements are between the S block elements and the P block elements. Next, why zinc, cadmium and mercury are not regarded as transition elements? Because they contain completely filled D orbitals in the ground state, okay, as well as in the common oxidation state. So they are not considered as transition elements. Clear? Next, what is the position of the D block in the periodic table? Give the group numbers of D block, write the valence shell electronic configuration. Okay, so position is in the middle of the periodic table, right, between the S and P block. Next one, give the group number is from 3 to 12. Next, write the valence shell electronic configuration, n-1 D10, ns 1 to 2. Okay, so that is there. Next question is, we'll go to some properties now. Melting point of transition metals increases up to D5 configuration and then decreases. Mercury is liquid at room temperature. Zinc and cadmium are soft metals with low melting point. Okay, so before answering these questions, some things that you should know. First of all, the hardness, okay, and plus the melting point depends on what? Metallic bonding. Okay, and the metallic bonding depends on number of unpaired electrons. Okay, now if you see, for the transition elements up to D5, what was happening? Number of unpaired electrons was increasing. D1, D2, D3, D4, D5, 1, 2, 3, 4, 5 unpaired electrons are there. When you come to D6, again the unpaired electrons decrease, 4, 3, 2, 1, 0, right? So up to D5, number of unpaired electrons increase, so metallic bonding will increase, so that is why hardness and melting point will increase, right? So that is the first answer here. You can see this is because up to D5 configuration, the number of unpaired electrons increases, right? So metallic bond becomes stronger and hence the melting point becomes higher. After D5 configuration, the pairing of electron takes place and the number of unpaired electrons decreases. Metallic bond becomes weaker and hence melting point decreases. Okay, clear? Next, mercury is liquid at room temperature. So if you see zinc, cadmium, mercury do not have any unpaired electron. If it is not having unpaired electron, metallic bond will be weak. If it is weak, then it is very difficult for this one to be available in the solid state, right? So that is why it is in the liquid state. So due to the absence of unpaired electron, the metallic bonding is weak. The next question, zinc, cadmium and mercury are soft. The same reason, that is due to the absence of zinc cadmium, metallic bond is very weak due to the absence of metallic bonding. Why the absence of metallic bonding? Because they do not have unpaired electrons. Clear? This one thing if you understand, you can answer all these questions very easily. Next, question number 4. Melting points of 3D series are less than 4D and 5D series. Okay, that is the first question. Even though a greater number of unpaired electrons are present in manganese, their melting points are less. So just now we discussed that if the number of unpaired electrons are more, metallic bonding will be more and melting point should be high, right? But manganese has D5 configuration, maximum number of unpaired electrons are there, but still its melting point is least in the periodic table, like in the 3D series. If you see the graph for this one, okay, the melting point first increases, then there is a drop and then it increases, right? And this drop is for manganese, right? So why does that happen? So let us answer them. So first question is, melting points of 3D series are less than 4D and 5D. So this is due to the higher enthalpies of atomization of 4D and 5D than 3D. Okay, enthalpies of atomization means the energy required to break the bonds, right? So as we go 4D, 5D, when mass increases, the enthalpy of atomization also increases. So in 4D and 5D, the enthalpy of atomization is more, so that is why melting point is more. Now coming to this question, the greater number, that is manganese. So that is, this is because manganese, technetium and Re have stable half-filled configuration. Now see, no doubt that they have highest number of unpaired electrons, but this D5 configuration is a stable configuration, right? Now if it is a stable configuration, what happens? Therefore electrons are held more tightly by the nucleus. Electrons are held more tightly by the nucleus. So delocalization of the electrons is less and hence metallic bond is weak. Okay. Now they have unpaired electrons, no doubt, but being the maximum number of unpaired electron, there is an additional condition to this, that it is also a stable half-filled configuration. Stable means what? It is attracted by the nucleus. Okay, the D5 configuration is strongly attracted towards the like this D5 electrons. Now these D5 electrons, because it is attracted towards the nucleus, it cannot participate in the metallic bonding. So metallic bonding becomes weak, melting point becomes low. Okay. Next is, why do transition elements exhibit higher enthalpies of atomization? Again, enthalpy of atomization also depends on the unpaired electrons, because D block elements have unpaired electrons, that is why they have high enthalpies of atomization. Enthalpy of atomization is maximum in the middle of each transition series. In the series scandium to zinc, the enthalpies of atomization of zinc is lowest. Enthalpy of atomization is more in 4D and 5D than in 3D. Give reason. So these are the questions and let us see the answer. So first of all, why they have higher enthalpies of atomization? That is because the number of unpaired electrons, they have stronger interatomic interaction and hence stronger bonding between the atoms, resulting in higher enthalpies of atomization. Okay. Next, enthalpy of atomization is maximum in the middle. So due to the more number of unpaired electrons in the middle of each series, the interatomic interactions are stronger, therefore the enthalpy of atomization will be maximum. Next, in the series scandium to zinc, the enthalpy of atomization of zinc is lowest, that is because of no unpaired electron, right? So the extent of metallic bonding of an element is proportional to the enthalpy of atomization. Due to the absence of these unpaired electrons in zinc, the inter-electronic bonding is weakest. So you just need to write due to the absence of electrons, unpaired electrons, okay. Next, enthalpy of atomization is more in 4D and 5D series. This is due to the strong metal-metal bonding in the heavy transition metals, okay. Next is question number 6. Okay, the E0 value for M2 plus 2M value for copper is positive. What is the possible reason for this? So we have just discussed that the value of M2 plus 2M for copper was positive because of high hydration enthalpy, okay. 1 second. Okay, the copper has high energy of atomization and low hydration enthalpy. Let me check this question once again. So let us see the next question here. The E0 of M2 plus 2M value for copper is positive. What is the possible reason for this? So now you see that the E0 value is affected by 3 factors. What is it? Enthalpy of atomization, enthalpy of ionization, and enthalpy of hydration, right? These 2 values are positive and this value is negative, means these 2 are endothermic, this is exothermic. Now if you remember, copper 2 plus, the electronic configuration is what? 3D9, right? So Cu plus is 3D10. So to go from here to here, so in this IE, there is IE1 plus IE2, okay. Now the second ionization enthalpy of copper and the atomization energy of copper is very high, right? So that is why these 2 together positive numbers is much more than this hydration enthalpy. So that is why the overall value comes out to be positive here, okay. Next, scandium has less E0 value. Why? So that is again, if you remember, I want to explain one concept here. See, if it is stable to unstable, okay, stable to unstable, if you are going stable configuration to unstable configuration, that means the element does not want to go, right? Element does not want this change. In that case, what will happen? E0 value will be less, okay. And if it does not want to go, then ionization enthalpy will be high, which we have already discussed in the previous question. Now if it is going from unstable to stable, unstable to stable, okay, then what will happen? Element wants this change. If element wants this change, then E0 value will be very high, ionization enthalpy will be low, okay. Now see, scandium plus 3 to scandium plus 2, it is having less value. So if you see scandium plus 3 configuration is of argon, right? It has a very stable configuration. Why will it want to go to the less stable configuration, right? It doesn't want. If it doesn't want, then it is E value will be less, okay. So you can say this is due to the extra stability of scandium plus 3, which has a noble gas configuration. Next, zinc has very high E plus 3 to M plus 3 to M plus 2 value. Very high value means what? If it is very high value, the element wants to go to that configuration. Zn plus 3 to Zn plus 2, right? What is the configuration? D9 to D10, right? This is from an unstable to stable configuration. D9 is unstable, whereas D10 is highly stable due to fully filled configuration, right? So when unstable to stable it is going, it is more the E0 value will be very high here, okay. So that is, you can see the highest E0 value for Zn is due to the stable D10 configuration. Let us see the next question here. Vanadium has relatively low plus 3 to plus 2 value, give reason. So again, that is due to M plus 2 should be more stable, right? M plus 2 is more stable because of vanadium configuration. So if you see scandium, titanium, vanadium configuration is 3D3 4S2, right? Now if you see vanadium plus 2 state is 3d3, okay, and this is exactly T2G half filled configuration. So this is a very stable configuration, okay. So that is why this is there. Now E naught of Mn plus 3 to Mn plus 2 value is comparatively high. So that is also you can explain here. Mn2 plus is having D5 configuration which is very stable. So that is why this value will be high. Next, Fe plus 3 to Fe2 plus is low. Now this is D5, this is D6, right? This is stable to unstable. If stable to unstable, that means what? The metal does not want, E naught value will go down, right? So you can see the values here. Extra stability of Mn2 plus, extra stability of Fe3 plus configurations. Next, question number 8. Among Zn2 plus and cobalt 3 plus, which is not attracted by a magnet. So here you should remember there are two types of magnetic substances. One is diamagnetic and one is paramagnetic, okay. So diamagnetic has no unpaired electron, whereas paramagnetic has unpaired electron. Let me write it nicely for you people. Okay, one second. Okay, so we have two categories, okay, diamagnetic and paramagnetic. So what is diamagnetic? No unpaired electrons, okay, and here we have unpaired electrons, okay. Now if there is no unpaired electron, then it will be not attracted by magnetic field and this one will be attracted by the magnetic field. Now you see Zn2 plus has no unpaired electron, not attracted, it will be Zn2 plus, okay. Zn2 plus will not be attracted. Next, Cu plus 1 is diamagnetic and Cu2 plus is paramagnetic. Again here Cu plus has no unpaired electron, so it is diamagnetic. Cu2 plus has one unpaired electron, so it is paramagnetic. Next, Sc salts are diamagnetic, again that is it has no unpaired electron, okay. So you can see here answers I have already given, you can check this, okay. Next, question number 9. Explain the color of the transition metals. Okay, so why do transition elements shows color? Okay, the first question, the answer here is very, very important. The color of the transition element is due to the presence of unpaired electrons in the d orbital which undergo dd transition, okay. These unpaired electrons undergo dd transition, they absorb the color from the visible region and undergo dd transition and radiate the complementary color. So the d orbital split, as you know, in coordination compounds, right. So these electrons undergo dd transition, they gain energy, go to the higher level, come back by releasing energy, right. So that is why they are colored compounds. Why Zn2 plus are colorless? For color compound you need to have unpaired electron, but Zn2 plus has no unpaired electrons, okay. Next, copper 2 plus salts are colored, that is because of presence of unpaired electron, okay. So remember this one, if unpaired electrons are there, then it will be colorful, okay. If no unpaired electrons are there, then it is colorless, or it can be sometimes asked as white color also, okay. Next, question number 10. How is potassium dichromate manufactured? So this is one of the very important question. You can see how many times this question is repeated. Direct question. First, iron chromate is converted to sodium chromate, sodium chromate is converted to sodium dichromate, sodium dichromate is converted to potassium dichromate, okay. So these reactions you need to remember, okay. Write down it, practice it again and again and remember these reactions. Next is question number 11. How does K2Cr2O7 reacts with I minus, Fe2 plus, Sn2 plus and H2S? So I'll tell you, I minus is converted to I2, Fe2 plus is converted to Fe3, Sn2 plus is converted to Sn4 plus and H2S is converted to S, okay. You can see the reactions here, okay. You have to write the complete reaction, so you need to not remember, you can write down I minus is converted to I2 and the basic reaction is this one what takes place, okay. Potassium dichromate converts to +3 from +6 to +3, okay. This basic reactions if you remember, then all others you can just write down as it is, okay. So these are the reactions, you can check here. Next is Okay, explain the oxidation of nitrite by acidified. So again the same reaction, like same question, oxidation of nitrite, oxidation of sulfurous acid. So let us see, nitrite ions are converted to nitrate ions, sulfite ions are converted to sulfate ions. Okay, clear? By potassium permanganate, not K2Cr2O7, this is by potassium permanganate. Okay, reactions please you have to remember. Next, how is potassium permanganate manufactured? So we have done a similar question in 2 marker also. So MnO2 is first, so MnO2 is converted to K2MnO4, that is manganate, then MnO2 is converted to MnO4, right? So you will get the reaction here. Okay, you have to remember this reaction, this is very important. Both the manufacture of KMnO4 and K2Cr2O7 are important questions. Okay. Next question number 14, how does KMnO4 react with this one? So same type, I minus I2, Fe2 plus Fe3 plus C2O4 gets converted to CO2. Okay, so this is the basic reaction that you should remember. Okay, in the in acidic medium, Mn plus 7 is converted to Mn2 plus. Now if I want to write the reaction, for example, MnO4, I'll write one and others you have to try. Okay, MnO4 minus plus 8H plus 5 electrons will give me Mn2 plus 4 water. Okay, this basic reaction you should remember. Now I minus will get converted to I2, right, by giving 2 electrons, right. Now you see the number of electrons should be balanced, right. So this electron, this will be multiplied with 5. Now if I write the total equation, it will become MnO4 minus, okay, plus you are multiplying this with 5, right. So I will get 10I minus plus I will be getting 8H plus. Okay, now this 5, okay, this one will also be multiplied with 2, right. So 2MnO4 minus 16H plus I will get here. Okay, I will get 16H plus here, then I will be getting 2Mn2 plus, okay, and 8 water plus I have 10I minus I have 5I2, right. This is the final equation that you need to write. So you can remember only one this reaction and then you have to balance the other. Clear? Similarly, Fe2 plus will be converted to Fe3 plus, right. So here you need to write that equation, balance the number of electrons and your work is done. Clear? C2O4 2 minus is converted to CO2. Okay. Try these questions and check your answer from the NCERT book. Okay. Next question number 5, how does KMnO4 oxidizes thiosulfate in neutral medium, iodide in neutral medium, manganese salt in neutral medium? This is also important question here. In neutral medium the reactions are different and in acidic medium the reactions are different. Okay, so thiosulfate is converted to SO4 2 minus, I minus is converted to I2 in acidic medium, but I minus is converted to iodate IO3 minus in neutral medium, and here the Mn2 plus salts are converted to MnO2. Okay, so these 3 reactions are very important, you need to remember these reactions. Next is, what are F block elements? Write the general electronic configuration. Why F block elements are called as inner transition elements. So in F block, what are F block elements? These are the elements in which, these are the elements in which the electron enters into the n-2 f orbitals or anti-penultimate shell and are called as F block elements. There are 2 series, that is lanthanides and actinoids. Okay, general electronic configuration n-2 f1 to 14, I'll write it clearly here, n-2 f1 to 14, n-1 d 0 to 1 ns2. Okay, next, why F block elements are called as inner transition elements? They are called as because in these elements the added electrons are entered into the anti-penultimate subshell. Okay, they enter to the anti-penultimate subshell, that is why they are called as inner transition elements. Okay, next is, what is lanthanide contraction, cause of lanthanide contraction, give 2 consequences of lanthanide contraction. So what is lanthanide contraction? The gradual decrease in the atomic radii from lanthanum to lutetium is called as lanthanide contraction. What is the cause of that? Poor shielding effect of 4f electrons. We have already discussed these questions. Now consequences are very, very important. You can remember 2 to 3 consequences. The first one is due to the lanthanide contraction, the atomic radius are same, and that is why it is difficult to separate them. Second one is the basicity decreases from lanthanum to lutetium, okay, because the gradual effective nuclear charge increases, so it is very difficult to remove OH minus ions, so that is why basicity decreases, okay. Next is question number 8, general characteristics of lanthanides. Just remember any 3 points. First one you can remember silvery white, then their hardness increases with the increase in atomic number, good conductors of heat and electricity, right. Next you can remember they are generally paramagnetic, except some elements are given which is having F0 and F14 configuration. Any 3 points you need to remember here. Next is what is actinoid contraction. Actinoids show greater number of oxidation states. What is the common oxidation state of actinoids? Okay, so what is actinoid contraction? The same thing. The gradual decrease in the size of the atoms of actinoids across the actinoid series is called as actinoid contraction. What is actinoids show greater number of oxidation states? That is because due to the comparable energies of 5f, 6d and 7s levels. Common oxidation state is same as lanthanoids, that is +3. Okay. Next, why cerium shows +4 oxidation state? What is the highest oxidation state shown by actinoids, or name an element which shows the highest oxidation state among actinoids? Okay, so cerium shows +4 oxidation state. So if you remember, cerium configuration is Xe4F4, right? But if it shows +4 oxidation state, it gets a stable or a noble gas configuration, so that is why it shows +4 oxidation state. Now the element of actinoid which has the highest oxidation state is your neptunium or plutonium, which has a configuration or oxidation state of +7, okay, Np and Pu. Next we have question number 21, that is give any 3 characteristics of actinoids. So as we wrote 3 characteristics of lanthanoids, you can remember any 3 characteristics of actinoids as well, okay. So the first one is all actinoids are radioactive, they are silvery metals, they are highly reactive in the finely divided state, they are paramagnetic in nature, okay, they have a common oxidation state of +3. Any 3 points from here you have to write down, okay. Next is give any 2 differences between actinoids and lanthanoids. So I have given you so many differences, you can remember any 2 points, which any 2 to 3 points for which you can easily remember them. So here this is very simple, 4f electrons enters to 5f electrons, all are radioactive. They are non-radioactive except PM. You should remember this can be asked as an MCQ question. Next you can write down they are less basic, they are more basic, okay. Lanthanide contraction is lesser, actinoid contraction is greater. Any points you can write down from here, okay. Next is study of actinoids is very difficult. Give 3 reasons. This question was asked in your I think blueprint paper also. So any 3 reasons. First is actinoids are radioactive, they have very short life, and they could be prepared in nanograms only. So very small amount of actinoids are present, so that it is very difficult to study them, okay. So yes students, one more question. Question number, this is 24, give some uses of DNF block. So in this way direct question will not be asked, but yes, on any one use the question can be asked, like 1 marker question or MCQ question can be formed from the uses part. So I have written some uses that you should know. The first one which you should be knowing is your AGBR, okay, very important. AGBR has special light sensitive properties in photography, okay, this is important. Next, TiCl with CH3Al Ziegler-Natta catalyst is used in the manufacture of polyethylene. This is important, you should remember. Next we have one more thing, yeah, nickel complexes are used in the polymerization of alkynes. You should remember this one. PDCl is used as a catalyst in the oxidation of ethine, okay. So these are certain things that you must remember. And one more, MnO2 is used in dry battery cells, and zinc and nickel cadmium are also used in battery cells, okay. So these all some important uses, just go through it, remember it, so that questions can be asked from this particular section, okay. So okay, so now coming to your week 3 schedule. So week 3 we are now on Thursday, right? So we have completed this one. Friday you will be having alternating current. Saturday you will be having maths and bio, integration and evolution, and Sunday also maths class will be integration part 2. Okay. Next is okay, in 1 second. Okay. So next, once again I want to remind you about the PU2 test series. Okay, PU2 Success Blueprint test series. It is a test series launched by Diksha, in which you will be getting 12 mock tests, okay, 4 part tests and 8 full length papers. You will be getting all the 4 subjects, that is PCMB. You can add on Kannada with that as well, and you will be getting exam focused question paper based on the latest syllabus, latest exam pattern, doubt clearing classes, one shot revision videos and video solutions of the questions. Okay, detailed explanation will be there. So if you want to know more, please go to the website. You can buy this at just rupees 599 after 50% off. So please do not delay, buy it as soon as possible because the prices may increase later, right? So this is going to be really helpful if you are an aspirant of PU2. If you want to target 95% plus and above, then this test series is a must for you. Okay, so do not delay. Go to the description section, click on the link, buy it as soon as possible, and remember the first test will be released on December 15. Okay, so before that please purchase it. Okay, fine, that's all, and I hope students you have enjoyed today's classes. I'll tell you, this 60-70 questions that we have discussed today is enough for your DNF block. Read down each and every question, write down them, learn the answers, because it is more about theoretical sense. So you do not have to you have to learn these questions. Definitely reactions, practice it again and again. Preparation of KMNO4, K8 CR27 is a must. Every alternative where this question is asked. So make sure that you prepare this chapter with these questions. Okay. Thank you for watching and see you soon in the next episode. Until then, prepare hard students. Date sheet is out. And if you need any other help, please comment down. I'll definitely address it. Thank you for watching and please subscribe the channel.